Hey everyone, and welcome to This Explainer. Today, we're diving straight into section 10.3 of our software engineering textbook, and we're tackling a massive question. How do we actually build highly dependable systems? You know, if you've ever stopped to wonder how things like passenger jets or space rockets manage to stay safe despite the sheer, mind-boggling complexity of their software, well, you are in the exact right place. We're going to unpack the fundamental engineering principles that literally keep our modern world running safely. So, let's jump right in.
Here's a quick look at our roadmap for today. We'll hit inevitable system failures, then define redundancy and diversity. After that, we'll look at dependable development processes, dive into the complexity trade-off, check out some real-world aerospace examples, and finally, wrap up with our summary and exam focus.
Okay, Section 1, Inevitable System Failures.
We really have to start with a fundamental, totally undeniable truth in software engineering. In any complex system, component failures are absolutely inevitable. Look, hardware eventually burns out, right? It has a physical lifespan. Software, no matter how rigorously we test it, will inevitably have some hidden bugs. And of course, humans are humans. We're always going to make mistakes during operation or maintenance. We can try our best to swap out hardware early or use automated tools to catch bugs, but we can never, ever eliminate these failures entirely.
So the ultimate engineering question we have to answer is this. How do we design our architecture so that a single failure doesn't crash the entire system? I mean, if a single burnt-out wire or one tiny software glitch can bring down a whole network, we simply haven't done our jobs properly. We need a solid strategy.
Moving to Section 2, Redundancy and Diversity Defined.
To answer that big question, we need to define the two core strategies of system dependability. These are basically the twin pillars of safety-critical systems. First up, redundancy. Redundancy simply means building in spare capacity, or duplicate components, that can seamlessly take over if the primary one fails. Think of it like a backup generator for a hospital. If the main power grid goes down, the redundant generator kicks in so the lights stay on. In our world, that might be a backup server that automatically spins up if the main server crashes.
But redundancy alone isn't always enough, which brings us to diversity. Diversity means ensuring those redundant backup components are completely different types. Why? So they don't share the exact same vulnerabilities. It's not enough to just have a backup. If the backup is an exact replica, well, whatever broke the primary system might just break the backup at the exact same time. By making them diverse, we practically guarantee they won't fail in the exact same way. The textbook has a brilliant everyday analogy to visualize this. Imagine you're securing your front door. Putting two identical locks on that door, that's redundancy. But if a burglar has the specific tool to pick that type of lock, they can just pick both of them, no problem. However, installing two completely different types of locks, now you've got redundancy and diversity. That single tool won't defeat both locks. The burglar would need different tools and different techniques, making your house significantly more secure.
All right, Section 3, Dependable Development Processes.
Now, how do we apply these concepts to our actual day-to-day software development processes? Because these principles aren't just for the final product, they totally apply to how our teams work. We use diverse validation activities, so we're not just relying on one single fault-finding technique. We'll use program testing to run the code, manual inspections where developers actually read through it, and static analysis, which is using automated tools to scan the source code for anomalies. And crucially, we deliberately utilize different team members for these tasks. By having one person write the code and a completely different person inspect it, we introduce a diverse perspective. That drastically reduces the chance that a human error slips through unnoticed.
So, quick micro recap. Failures are going to happen. It's just a fact of life. Therefore, we must deliberately engineer both our systems and our processes with redundancy and diversity to maintain safety.
Which brings us to Section 4, the Complexity Trade-off.
Here is where it gets tricky. Implementing all these safety mechanisms introduces a massive complication, because in software engineering, nothing comes for free. Adding diverse backups means writing a lot more code and adding complex switching logic. Imagine having to write 3 completely different programs to do the exact same job just in case one fails. A common misconception for newer engineers is that adding backups automatically makes a system safer. But ironically, this massive increase in complexity creates brand new places for unexpected bugs to hide. Because of this, some engineers argue we should avoid diversity entirely. They say we should design the software to be as simple as possible and pour all our resources into extreme, rigorous verification of that one simple, identical system.
Let's see this in action. Section 5, Real-World Aerospace Examples.
It's fascinating to see how the aerospace industry handles this exact trade-off between complexity and simplicity.
literally where theory meets reality at 30,000 feet. The Airbus 340 fully embraces complexity. They use redundant and diverse systems, different flight control computers, processors from different manufacturers, and software written in completely different programming languages by different teams. Boeing, on the flip side, uses redundant hardware, sure, but they run the exact same software on all of them. The Boeing 777 philosophy emphasizes extreme simplicity and rigorous validation, actively choosing to avoid the massive complexity that diversity brings.
Let's pause to emphasize a really vital takeaway here. Both of these approaches are highly successful in commercial aviation. Both the Airbus and the Boeing are incredibly safe aircraft. This proves that you can achieve highly dependable systems through entirely different engineering philosophies.
But when this balance goes wrong, disaster strikes. Take the infamous 1996 Ariane 5 explosion. The European Space Agency launched this highly anticipated rocket, but the primary software encountered a numerical overflow bug, essentially trying to cram a very large number into a space that was just too small. The backup system immediately switched on, which is great, right? That's redundancy. But the backup was an exact replica running the exact same software. It lacked diversity. So it hit the exact same bug milliseconds later, and the multi-million-dollar rocket exploded just 37 seconds into flight. It is a tragic, perfect example of redundancy completely failing because it lacked diversity.
Okay, finally, Section 6, Summary and Exam Focus.
Let's wrap up this explainer by highlighting exactly what you need to know for your upcoming exams. Make sure you can clearly define redundancy as spare capacity and diversity as using different types of components. You absolutely must be able to contrast the Airbus and Boeing design philosophies, how one uses diverse software while the other relies on simple, identical software. And you're ready to explain the fatal lack of diversity in the Ariane 5 failure. Getting a solid grip on these core concepts perfectly sets us up for our next major topic, reliability engineering.
I'll leave you with this final, provocative thought. As a software engineer, you will never build a perfect system. It just doesn't exist. Instead, you have to master the delicate, high-stakes trade-offs between complexity, redundancy, and simplicity. How will you choose to balance your architecture when lives are on the line? Think about that. Thanks for joining this explainer, and I'll catch you in the next one.